the direct power method provides the maximum magnitude eigenvalue and the corresponding eigenvector. In fact, we can tweak that method to find out the minimum magnitude eigenvalue and the corresponding eigenvector also. So before we get into it, how we are going to do that, it is better to see an interesting property with this eigenvalue problem. That is, suppose the problem we are addressing is a dot x will be equal to lambda of x, where lambda is the eigenvalue and x is the eigenvector. This is the problem we are dealing with. Let me take A inverse of this matrix and multiply the A inverse from the left. So what am I going to do? I am going to take A inverse and multiply this A inverse with A, and let me take it as x. So this will be lambda times A inverse dot x. So now this is identity matrix. So therefore this is going to be, so this will be, this will be x is equal to lambda into A inverse. So I can rearrange this matrix as A inverse dot x will be equal to 1 by lambda times of x. Or if I call this 1 by lambda as lambda inverse, so then I can write it as A inverse of the matrix x will be equal to lambda inv, let me note it as inv, and x inverse. Now, x vector. So now this is an interesting relation. What it says is, the eigenvector of the matrix A is also the eigenvector. This is eigenvalue problem, correct? So the eigenvector of the matrix A is also the eigenvector of the inverse of the matrix, and the eigenvalue corresponding to any eigenvector will be and the equivalent of that eigenvalue corresponding to the A inverse will be just 1 upon that eigenvalue. Or in fact, if I find this is the, if I had a matrix A inverse, and if this is a lambda inverse is the eigenvalue, the corresponding eigenvalue corresponding to this vector x for the matrix A will be 1 by lambda inverse. Okay, so now, so this gives an interesting way. So now if I use this method, this problem using the direct power method. So what am I going to do? I am going to solve this using a direct power method. Then what it's going to give me is, it's going to give me the maximum magnitude lambda inverse and the corresponding eigenvector. So now maximum magnitude lambda inverse is nothing but the minimum of lambda of A mean, because lambda inverse is 1 by lambda. So when this becomes maximum, this becomes the minimum. So this way, when I solve this using the direct power method, so what we'll get is, we will get a lambda inverse max, and 1 by lambda inverse max will be the lambda min of the matrix A. And by this method, we can find out the minimum magnitude eigenvalue and the corresponding eigenvector x. Now, so how do we proceed? One simple and straightforward way is to find, given a matrix A, find the inverse of the matrix A, then use the same algorithm what you develop for direct power method and get the maximum magnitude of eigenvalue, take a 1 upon that, that's what your minimum magnitude eigenvector of the matrix A. But no, only thing is we can still, and how we are going to find the inverse of the matrix, we have found, we have discussed all these methods to find inverse of the matrix in the earlier classes. So, and in fact we can rearrange, peek around this equation, and somehow we can avoid finding the inverse of the matrix. How we are going to do is, so let us see how we proceed this in the direct power method. In the direct power method, how we start with some arbitrary x, multiply with matrix A, and that will give you, say, something y1, and which we scale it out to x1, correct? So which we scale it to x1. So in the second case, what we are going to do, a square, correct? So a square of x, and that will be a dot, and if I scale this to, if I scale it to x1, So this will be x1. And this we'll call it as y of 2. Correct? This is the way we perform the direct power method. So I keep on doing that. So finally what I am going to do is say something around a of kth power of this matrix A into x will be A matrix into the scaled previous value. Correct? So that will be what? X of this is k, so this will be k minus 1, and this we call it as y of k. And the next will be, so if you find out the next one, so next will be a x of k will be y of k plus 1, and this way we can proceed. So now, so let me take out this equation, any one of the equation. Let me take out certain this equation for example. So if I see this equation, what we are having is A matrix multiplied by xk. Oh, sorry, this is the inverse we are doing. We want to do it with the inverse of the matrix. Okay, because we are doing the inverse power. Okay, so this is what this will be. A inverse dot xk, which is the scaled previous vector, will be equal to y of k plus 1. Now if I see here, this is the quantity which comes from the earlier iteration. So I can rearrange this equation and I can write it as, so take a this side. So what we are going to have is a, when I multiply by a from both the sides, so what am I going to get is a dot y of k plus 1 will be equal to x of k, kth iteration. And this is an interesting algorithm. So why this is interesting is, so the same problem. Now in this problem, A is the one we are given the matrix and x comes from the previous iteration. From the previous iteration x comes from, and what we want to find out is y of k plus 1, and that's what, and then we scale it up and go for the next one. So for us, this is the unknown. So here A is given, x is given, and the unknown is y. I should write it here. Unknown is this y. So, and so we know this is simply a matrix equation where A dot x equal to b, which we solved in earlier classes. So, and one way to solve this matrix is decompose your A into L dot u, that's LU decomposition, and then we use a back substitution, forward substitution, that will give us y, and from the y again you scale back, get the x, then again use LU decompose LU and keep doing it out. In this process, we once see when the matrix is given, you decompose the matrix into L dot u and keep it stored there and start with the arbitrary x and keep on doing. So every time you have to do this LU, that back substitution and forward substitution, and find out y of that particular iteration, scale it back, put it back again as a b vector in early decomposition, and you can do it out. So this way we can find out the minimum magnitude eigenvalue and the corresponding eigenvector. Okay, so fine. And so this method is called as the inverse power method. Okay, so by direct power method, we get the maximum magnitude eigenvalue and the corresponding eigenvector, and the inverse power method, we get the minimum magnitude eigenvalue and the corresponding eigenvector. Fine.